Okay, I'm back on uh, the topic of the variational method for estimating the ground state of Hamiltonians that we don't know how to solve from first principles. Please forgive the background sound. That's just my heater, and I expect it'll go off here pretty soon. Now, there was one dangling issue that's left over from the last lecture that I wanted to cover just to touch on before continuing. We were doing the ground state of hydrogen as an example, for which we know the exact result, and that's written here. For the ground state, we have just n is equal to 1, and so the 1 over n squared becomes 1. Then we have this coefficient, which evaluates to negative 13.6 eV. Now, to do an estimate without knowing the actual ground state wave function, I suggested that we start off with a three-dimensional Gaussian of a variable RMS width, and we would use that RMS width as a variational parameter later on after we've evaluated the Hamiltonian in that Gaussian eigenstate, and by minimizing that Hamiltonian with respect to that parameter, find our best, although still overestimating, estimate for the ground state of hydrogen. And last time I got kind of confused by my failure to find a factor of 2 or find exactly what this normalization factor is on my trial wave function. And so I just want to go back over my notes. I did have it right in my notes, and I just want to remind you how to get it. So here's the coefficient that represents a Gaussian, the wave function, e to the minus r squared over 2 sigma squared. Sigma squared is, of course, this variational parameter we're going to play with after we're done. What coefficient is it that I need to put out here in front in order to make this psi, when I square it and integrate it over all three space? 1. And the easiest way to do that is to switch to Cartesian coordinates. Then r squared becomes x squared plus y squared plus z squared. Since it's in an exponent, it becomes three factors: e to the minus x squared over 2 sigma squared times e to the minus y squared times a similar factor for z. And now the 3D integral breaks down into an independent product of three independent integrals over Gaussian factors. X goes from minus infinity to infinity, y, and z. So let's just do the x one. Turns out that because I had to square this factor, instead of looking like e to the r squared over 2 sigma squared, it looks like e to the minus r squared over sigma squared. That means that my standard deviation actually turns out to be sigma over root 2. So the result, the familiar result for the Gaussian integral, square roots of 2 pi sigma squared becomes, because sigma squared is actually sigma squared over 2, square roots of pi sigma squared. And since I need to take that factor out to normalize it, here it appears on the bottom, pi sigma squared. And that all should appear inside a square root for the x integral. And then similarly for the y and the z, if I take all three of them as a product, then I get cubed. Now it should be square root, so it would be 3/2, except that the psi gets squared before I do the integral. So I split that normalization factor 50% for the psi star, 50% of it for the psi, and I end up with this pi sigma squared 3/4. That's the correct answer. And there's lots of other ways to get it, but anyway, the easiest way is generally the one that's least error prone. So what happens to the result? You'll have to go through and modify what I did, because I think in class that I had a square root of 2 on the top here. But if you go through, nothing changes in anything that we wrote, except that square root of 2 is missing. So now you can see when we do the angular integral to get t, there's no angular dependence. And so you just do the integral over d sigma d cosine theta, and we get 4 pi. Just don't forget that we had to have that factor of 4 pi because we didn't explicitly write the y00 in the wave function form when we wrote it down. We implicitly included it because it's a constant. Now, when we do this integral all the way out, we get t, and here's the final value for t, 3/4 h bar squared over m sigma squared. And likewise for v, which I think we did in class, but probably again mistaking this factor. Watch all the factors. We actually need this 2 here, and then the square root of pi sigma on the bottom. You can follow your way through these notes on your own time. I don't mean to repeat that whole lecture, just to show where that constant coefficient comes in. So when you work out, the only thing that's going to change now is the coefficients beside the t and the v have now changed, one of them getting a factor of 2, one getting a square root of 2 or so. You can check it. And when you set the first derivative to 0, now the coefficient is somewhat different than you had in your notes, which is this 4 over 3 root pi. Now if you put that in your calculator and you combine it with the other term, we end up with negative 0.42. And that is a number that's close, even closer, although still an overestimate, to negative 0.5, which was the exact answer. All right. So in fact, when we do everything carefully, we see we got even closer to the ground state energy, albeit with some error, and that's at the level of 20% or so, which is not too bad, considering the fact that we didn't really scrutinize the potential very closely by picking the Gaussian, because if we had scrutinized the potential, we would have realized that maybe it would have paid off to pile up more of the wave function's intensity in the middle, right there at the point where the potential goes to negative infinity, which is the way the true wave function psi 1, 0, 0 behaves. This is the e to the minus r over a behavior of the true Gaussian wave function that actually has a cusp here, kind of a peaking point when you cross through r equals 0. Whereas the Gaussian is smooth and has a 0 slope. Nevertheless, it kind of makes the point, doesn't it, that you don't have to know all very much about the details of the shape of the ground state to get a pretty good idea of what the energy of the ground state is. So there we have finished with doing problems we know the answer to. Now let's attack a problem we don't know the answer to. Moving on now to lecture 9. This is our first attempt to do a problem where we don't know the answer. Nobody knows so far how to solve this problem analytically. So we are now trying to use an approximation method to get an analytical estimate for a problem that we don't have the analytic exact answer to, although we do have an experimental result. So by comparing with the experimental result, we'll be able to see how close we are to the true ground state as we approach it from the top. So this is going to be the helium atom. Helium has 2 electrons and 1 nucleus with charge +2. Nobody knows how to solve this problem exactly using an analytic formula. Maybe one of you will end up being able to solve that analytically, but so far no success. So what's the best attack? The variational method turns out to be a very powerful way to attack these kinds of multi-body final states, because one has some idea of how to start it. You can start it by treating the problem as if the electrons didn't know about each other and each one of them independently orbits the center, the nucleus. If one treated the problem in that fashion, one could get an exact result. You know how to solve the hydrogen atom, and if it were helium plus with just 1 electron, one would just turn back to the hydrogen atom again and double the charge of the nucleus. That would mean that instead of having e to the 4th, where do we get e to the 4th from? Well, remember that alpha squared in the binding energy of the ground state? That had 2 powers of alpha, each power of alpha having an e squared in it. And where did the e squared come from? Well, one of the e's came from the electric charge of the electron and the other from the charge of the proton. So if I double the charge of the nucleus but not the electron, then 2 of those e's get factors of 2, and 2 of them remain the charge of the electron. That's why the binding energy of helium plus is 4 times the binding energy of hydrogen. So if we could do the problem that simply, then you would just say, well, the first electron comes along and it binds with 4 times the binding energy of 13.6, so multiply 13.6 by 4, and you end up with a binding energy, whatever that is, something like 50 MeV. Then bring along the second electron. Well, if you could ignore the charge of the first electron, the second one would bind with the same energy. Pauli doesn't mind 2 electrons because of spin being in the ground state. And so we would end up with something like 110 MeV of binding energy. And that's a sort of cartoon version of what the ground state of helium looks like. But I'm afraid we've violated one very important principle, and that is that if you take into account the electrostatic attraction, that is the nucleus-electron interaction, you cannot ignore the electrostatic repulsion that you get along with it, because the 2 electrons don't like being nearby each other, and they're forced to be by pulling them all into the ground state near the nucleus. So let's write down the actual Hamiltonian and see if we can get a variational guess for what that ground state wave function might look like, so that we can get started with this problem. So here we go. 2 particles, therefore 2 equal kinetic energy terms, p squared over 2m twice, 1 for the first particle, 1 for the second. And I put a subscript there just to remind me that when I turn that into a derivative, it's a derivative with respect to x1 on this side and a derivative with respect to x2 on this side, and it's acting on a wave function that lives out here that has 2 coordinates in it, an r1 and an r2. That is, it's a function of 6 coordinates. So when I write down the potential, I'm actually writing it as a function of 6 coordinates as well, of the 3 coordinates of the first electron and the 3 coordinates of the second one. What is the explicit form for V? Well, I said it already. We have a doubly charged nucleus, and so the product of the 2 charges, rather than just being E squared, is 2E squared. There's the negatives because it's attractive. But then inside, we write 1 over, inside the radial dependence, we have 1 over R1 plus 1 over R2. And I've written it here by putting them over a common denominator. Now, let's not forget that there's a positive repulsive interaction between the 2 electrons. That actually goes like 1 over R minus R2, R1 minus R2, and that is a quantity squared. So first we take the vector difference of their 2 positions, and then take the magnitude before we take the reciprocal. Turns out that if we could make the Hamiltonian divide into 2 pieces with a plus in between, then, and the first piece depended only on R1 and the second on R2, then we could call it sort of an independent decoupled 2-particle problem, and then we could solve each one by one, and then just make the product of those 2 wave functions and call that the ground state, or we call that the eigenstate. And it almost works, because look at this. I can take the P1 from the kinetic energy term, and I can take the first one, the 1 over R1, from the potential energy term, and I can put those 2 together and call that H1. Let's finish by taking the same thing with the second particle and write that and call that H2. What have I left out? Just this interaction term that doesn't factorize. It doesn't just split into a piece that's only got R1 in it or only got R2 in it. That's going to be the problematic piece. That's why the problem is so hard to attack analytically from first principles. So at least if we can't solve the whole thing, we can start off by making ourselves a Hamiltonian that consists of the pieces we know how to solve, H1 plus H2. And what did I say earlier? If I know how to write down the single particle ground state for the H1 in terms of just the coordinate R1, and similarly the coordinate of R2, which is the eigenstate of H2, then if I make the product wave function by just sticking them side by side, here's the ground state of the ordinary hydrogen atom, that is the eigenstate of H1 for the minimum energy, and similarly putting it right next to it, the same thing for H2, and these are just these 2 hydrogen ground state wave functions. Then I can see that this state here with the superscript 0 is an exact eigenstate with the minimum energy of H0, And since each one of these contributes a negative 4 times 13.6, let me write that the H0 acting on psi 0 has negative 8 E0. And remember, my E0 is just the ionization potential of the hydrogen atom. What have I left out? Here's my potential V12. I wrote that up here. That term right there, now called V12. Okay, so now let's concentrate on the difficult part. We know what H does in this piece. That's very easy to write down. Let's now concentrate on the V12. And we're going to be needing to take the expectation value of this operator inside the trial wave function. And so you can already guess, I'm going to take this psi 0 as my trial. Now, maybe you're going to say, where's the variational parameter? Well, I haven't got to that yet. We'll come back and we'll decide what's variational. For the moment, let's just see if we can actually evaluate H prime, this V12, which I here call H prime, inside these simple product wave functions, sandwiched on the left as a bra and on the right as a ket. Okay, so if I take my coefficients, I put together the square root of 2 square root of 2 and these two factors of 2, that's 8 over pi a cubed. So there's my normalization factor. This coefficient here comes from the repulsive interaction of V12. The only thing I have to worry about in doing inside the integral is the 1 over this R1 minus R2. Now, it's not all that productive for me to walk through the algebra. You can know how to do this integral. You convert this R1 minus R2 into the square root of the distance between two vectors. And I'm going to adopt the z-axis to be along one of them. And I'm going to do the R2 integral first, which means that R1, while I'm doing the R2 integral, I'm going to leave R1 fixed. So since we haven't decided what our coordinate system is for R2, let's adopt a coordinate system in which the z-axis is along the direction R1. And I can always do that because every time I change R1, I repeat the R2 integral all over again. And so I have a choice once again to choose where my z-axis is when I do that integral. So I'm going to just choose the z-axis along R1. That means then that when I do this difference with the absolute value bars, it's fairly simple. I have R1 squared length of R2 squared minus this difference, and this cosine theta, which normally would be the theta 1, 2, the difference between them is actually, because I've adopted the z-axis along R1, just the theta of R2. It's the polar angle of the direction R2. And what I'm calling I2 here is just that integral. Start here, go to here, okay? And I'm going to fix R1 and just do the R2 integral. I'm going to call that I2. So here it is. I've left the constant factor e to the minus 4R1 over A outside the integral. So just the R2 piece, the piece that I have to consider as I do this integral. And here is the standard three-dimensional volume element, R squared dr d cos theta d phi. Okay, so the easiest one to start with is phi. That's done. 2 pi. No dependence on azimuth. The second piece that's the next most easy is cos theta. Notice that there's no cos theta in this term. It all appears right here to linear power, which is great because I know how to integrate that by I. I just make that, since that's the square root on the bottom, its integral is the square root of the same factor on the top. And I have to divide by R1, 2R1, R2. You see the negative there that has come out to switch the order of my bounds, which I've now reversed, made from pi to 0. Normally they would be from cosine theta equals -1 to +1, and I've reversed them. That gets rid of the negative sign. The factor of 2 disappears when I bring down the 1/2 to take the derivative. Anyway, all of that's correct. So now I'm going to evaluate this. Last thing I have to do is the radial integral with that factor. So let's go to the next page and do that. Okay, too far. Good. So here I am now evaluating this square root at the two bounds of pi and 0. And when it's pi, the negative becomes plus. And when it's 0, the negative remains negative. And so look at this for a minute. That's a perfect square where I use R1 plus R2 lengths. Okay. And so this is actually the absolute value. Since I'm interested only in the positive square root, it's the absolute value of R1 minus R2. And so we end up, when I take this difference, to have two possible outcomes. One is when the absolute value has a plus sign, when you take it outside the absolute value, that's when R1 is greater than R2. And in that case, then, when I subtract, okay, the thing that changes sign is the second term, R2, survives. And I end up with positive 2R2. On the other hand, if the absolute value, when I come outside it, becomes negative, I switch the sign, that becomes plus, and I keep the other term. So which one of these survives, and that's the difference, just depends on which one is greater. So here I'm writing it more explicitly. Here's my factor, 4 pi e to the minus 4 R2 over A times 1 over the greater. And whichever one is greater, if it's R1, stick R1 there. If it's R2, stick R2 there. Got it? Okay, now it's time to do the radial integral. Because I have this kind of split 2 value from the cosine theta integral, I have to split my radial integral into two pieces. First, when R2 is the lesser of the two. In that case, when R2 is the lesser, I choose this top one, and it's 1 over R1 that comes outside the integral and sits here. And the rest of the integral just is evaluated straightforward fashion. Now, what happens out here? Well, in this case now, the R2 is what survives and has to stay inside. It kills one of the powers of R2 that came along with the R squared dr volume element. And this is quite different integral, but since we know how to do these Gaussian integrals really well now, I'll just write the result. Here I am converting from a dimensionful radial coordinate into a dimensionless x coordinate by rescaling things with 1 over a and factors of 2. Now you can see this integral you can look up in Wolfram Alpha, this one as well. If you don't like looking things up in Wolfram Alpha, you can do it from first principles. Here I show how to use a trick. Just by differentiating with respect to alpha, you can do any power, any even power, or actually any odd power, because this is not a Gaussian integral, it's an exponential integral. Anyway, follow through that. This is just evaluating integrals in a straightforward fashion. And here now I'm plugging in the result. Okay, finally, after summing up and making cancellations of terms that cancel, we end up with this term here. Notice a constant coefficient with a 1 over R1 in it. We haven't done the R1 integral yet, so keep your eye on that guy. And then the other factor of R1 appears here in this exponential factor, e to the minus 4 R1. And there's an R1 in the coefficient, in this polynomial coefficient. All right, so now this final result belongs inside the R1 integral, which is the last piece we have to do. So let's carry on. If you'll go down, please. Okay. There we are. Okay, so here now putting everything together, you can see this coefficient that came along with the normalization of the wave function itself. This came along with the value of V12, the coefficient for the electrostatic repulsion potential. And now we get to start sticking in the factors from the integral. Here's the angular integral piece, 4 pi, from the R1 integral. And this is the radial R1 piece. And we were careful to preserve all of those terms in that expression that we wrote last time. Notice, though, that the 1 over R1, just from the last line on the previous page, has become R1 to the top because our volume element had an R squared dr1 in it, and that 1 over R1 killed 1 power of that. All right, carry on. What do we end up with at the bottom? Finally, summing all the pieces up, we end up with 5/4 h bar squared over ma squared. Now we recognize this, that has the units of energy, and we recognize that as just twice the 13.6, okay? And so I can rewrite it by writing it as 5/2 times this 13.6 E0. And if I put that in my calculator, it's about 34 eV. So let's combine everything we know. There's the -8 from what I call the naive Hamiltonian. Here's the new piece that we got from considering the repulsion, which is positive and takes away some of the binding energy that the -8 gave us. Put it all together, and we get about -75 eV. Very interesting, because what's the answer from experiment? -79. Notice that just by this kind of simple-minded saying, what if the electrons didn't repel each other? We actually end up with a number that's within 5% in the ground state binding energy of helium. And of course, we can do much better. So if you look through the problem in the homework, I think it's 7.7, you're actually being asked to do this again. For a hydrogen minus ion, that's an ion with just one proton in the nucleus and then 2 electrons orbiting it. It's the same problem, except instead of having a doubly charged nucleus, it's the singly charged nucleus. And then you're asked to do it again for lithium, which has 3 positive charges in the nucleus. So it's kind of like repeating this whole process again. Now, there's a little more to it than there's a way to use this a little bit more powerfully than the way I showed, because here I didn't have a variational parameter, did I? I just sort of naively assigned a frozen wave function form. But now if we go back, and you can review how this happens in the book, if you go back to the original wave function that we put down, that product with the R1 piece times the R2 piece, and you say, yes, but maybe that Bohr radius that you put in there isn't the real Bohr radius that you would have just with one electron, because the 2 electrons kind of shield, one of the electrons kind of screens the charge of the nucleus. So maybe instead of the electron seeing the nucleus charge of +2, what if it only sees like +1.8? Maybe the other electron kind of gets in the way and clouds how much charge the average electron can see there in the middle. So maybe we'd do better by sort of compromising between +2 and +1 and say maybe it's 1.5. And what you can do, and the book shows how to do it, is you can sort of move some of the charge out of the H0, and then your binding energy goes down. So instead of being 8 times 13.6, it becomes 8 times, maybe 10.5 or something like that. That decreases the binding energy because the nucleus is not quite a +2, it's a +1.8, and that's a variable. But then you have to put the piece you took out of H0 back into the H prime. Anyway, look at how that's done. You don't have to do any new integrals. It's nice. Okay, so you basically use the results that are right there on the page in front of you, but now you imagine the A that you put in the expression for the trial wave function to be a variable instead of just the Bohr radius. It's the Bohr radius divided by some factor Z. Okay, and then that factor Z becomes a variational parameter, and as you increase the screening, you lose binding energy from H0, but you gain it in the H prime. And there's this trade-off, and you can take the derivative with respect to Z, and you end up with a new variational but ground state energy that's even closer. So I think, as I remember, it's -78 electron volts, and the experimental answer is -79. Amazing how close you get with such simple-minded approach. And so you'll have a chance to practice that. I don't want to do the homework for you. Go ahead and look at how that trick is played by reviewing the material in the book right before problem 7.7, and then do it for your homework. And so that's all I had for today. And the homework will be due on Monday or on Wednesday if I'm not back in time. And I'll make sure I let you know by Saturday night which way it is going to go. Okay, so I'll see you soon. Bye-bye.